Okay, so for our second talk, we have Tina Kanstrup, and she's going to talk to us about link homologies and Hilbert scheme via representation theory. Thank you, Tina.
Thank you very much. Thank you for the invitation. And thank you to Jose for introducing the braids, which will be like the cornerstone of what I'm going to talk about. So the idea of this project, which is joined with Roman Basukavnikov, and I also discussed it quite a bit with Alexei Oblomkov, is to try to unify some of the different approaches to Korona-Rosansky triple graded link homology, because this is a field where you have like, oh, there's a conjectural instruction in this direction in terms of circle bimodules, matrix factorizations, and all sorts of stuff. So this project kind of like connects together at least some of those, or two of those. So let me just recall the construction really briefly. So circle bimodules is already featured quite prominently, especially in Ben's talk. So I won't spend a lot of time on it. I'll just like quickly recall the definition. So we fix. So okay, so this is only going to be type A. At the end of the talk, I might say a few words about other types, but I kind of imagine I'll run out of time before then. Okay, so the idea is you take a polynomial ring in n variables, and you put each of the variables in degree 2, and then for you have an Sn action, and each simple reflection, you define Rs to be the polynomials, which is fixed under this permutation. And then you define your circle bimodule corresponding to this reflection in this way. And the entire category of circle bimodules is then the smallest full subcategory of R graded bimodule, which contain R, and all of this for different simple reflections, which is closed under direct sums, tensor products, grading shifts, and direct summons. And as well, the mean thing of this is that this categorifies the finite Hegg algebra. But for the purpose of my talk, I only need like these kind of simple things, because what I need is what's called Rukia complexes. So I want to build something corresponding to a braid. So I need to say, okay, what do I do to a positive crossing, or what do I do to a negative crossing? And this is the answer. I have this two-term complex whenever I have a positive crossing, and I use this two-term complex when I have a negative crossing. And if I like take a braid, then I just fix some decomposition of it, and then I take all of these corresponding and tensor them all together to get a giant complex. And by theorem of Ruki, these satisfy braid relations. And triplet graded homology is then, well, if having like a giant complex with 2 to the number of crossings parts wasn't enough, then you can take to each of the terms in the crossing, you have to take Hawkshaw cohomology, which is defined like this. And then your triplet graded homology would be to take Hawkshaw cohomology of each of the terms in your giant matrix, and then take the homology of this complex. And this is something that can be done in only very small cases or very lucky circumstances. So I generally think people turn to geometry in order to see if there is some geometric formulation that will make this easier to deal with. And there is. So all of this is type A. So just to fix notation, I'm like, it means that I will be working with GLN, and my Borels, which is upper triangular matrices, And similarly with the Lie algebras of the corresponding groups. So frac G is all matrices, and B is like all matrices which are upper triangular, and N is strictly upper triangular matrices. Okay, so now I'm gonna draw my world map, so to speak. So my starting point of everything is a braid, and the construction that I just cited for you, this triply graded homology, well, what did it do? It take to a braid, it associated this giant Rukia complex, and then it took this term Y as Hochschild homology, and then took volume of the whole thing. And this landed us with a triply graded vector space. Okay. But there's other ways to do this, to get this construction. One of them is using matrix factorizations. And this is due to Oblomkov and Lasansky. So this is a geometric construction. So basically this diagram I'm going to draw is like my entire talk, and the rest of the talk will just be spelling out what the different parts mean. So I will, in a moment, tell you what a matrix factorization is. For now, I'll just write the space. And then this thing comes with the data of a potential. And once I'm done drawing my diagram, I'll explain what this really means. Okay, so what they do is they take a braid, and to this, they associate a matrix factorization, whatever that is. So let's just denote the corresponding matrix factorization by C beta. And then they have a functor, which they denote as the Chern functor, stable on localization, which goes into periodic complexes of C star cross C star equivariant coherent sheaves on the Hilbert scheme of endpoint in C2, which maybe I should recall what the space is. So usually people write it in terms of ideals in C, X, and Y of codimension n, but the more convenient way for me to write it is the following way. So I take two matrices and a vector, and I require those two matrices to commute, and then I require that if I take any combination of these x's and y and apply it to my vector, then I should be able to produce all of Cn. And then I mod out by G. Okay. And then it is a theorem by Oblomkov and Lasansky that this also computes triply graded homology when you take this vector and here you tensor with the exterior algebra of this trivial vector bundle with fiber Cn, and then take homology with the structure sheaf here. And this kind of is inspired by maybe the maybe most famous geometric conjecture about triplet graded homology in the GNR, which talks in very similar terms. So GNR considers not exactly the Hilbert scheme, but a cousin of it, which is called the Flack DG Hilbert scheme. So the conjecture is that you have a functor from complexes of circle bimodules to coherent sheaves in the space, such that when you take cohomology of this sheaf, this calculates for your triplet graded homology. And also part of the is that in fact there is also an adjoint functor in the opposite direction, which is monoidal. Okay, so this is kind of the state of things. So now I'm going to relate those two, because this is like an explicit construction, which is inspired by string theory, and it's not as such by any means clear what does this have to do with any of this, only that's the brain, like the end of the day, they compute the same thing. So like, why do they compute the same thing? So maybe before I say that, I should tell you what this is. So it's kind of the Flack Hilbert scheme is something where for your Hilbert scheme, you had ideals, you now have nested ideals. And in the kind of similar way of writing things as I did for the Hilbert scheme, this kind of maybe slightly non-standard way of writing it, I can write it in the following. So I have two matrices again, but now I have a Flack. So this other second matrix is supposed to be nilpotent, and this is what you usually indicate by this C here. And then F is the Flack, so the Flack variety. So this is just a Flack of vector spaces. So one vector space, a series of vector space contained in each other, with one being one dimension bigger than the other. And then we have this kind of vector as with the Hilbert scheme. And then we require that my X and my Y fixes the Flack. This is the Flack, and I have the same stability condition. This is called the stability condition as before. And I also want to require this. But this is where this DG stuff comes in, because this is a really nasty space if I just do that. So the canonical way of dealing with really nasty things of this form is you take what's called a derived fiber product. So this is just a fancy way to impose this condition. You could have imposed this condition in the same way here, but since this is so nice, it will turn out to be the same thing. But it matters on this space, whether it didn't matter here. All right, so now let's see how we can relate these things. Okay, so the ones like standard or the geometric avatar of circle bimodules, or maybe one of the more classical, other classical geometric categorifications of the Hecke algebra is in terms of D modules. So be equivariant D modules on the Flack variety. So we have a way of going from here to here. So, but now we can do something, because, and I'll explain this a little bit later. We can take what's called an associate graded, or related to associate graded, which I will say some more words about later. And this takes us from D modules on the space to coherent sheaves on its cotangent space. And this is the space, which is the Steinberg variety, which is usually written this one where n tilde is the star of G mod B. It can also be written as G times n over B. Okay, and so now you can, I will construct that there is a natural map going to a space that kind of looks a little bit like the flag Hilbert scheme. Which takes G and then this n tilde, and then I'll put a superscript commuting, meaning that, so this has a matrix in it. The adjoint action of my G on my X is one matrix, and then my matrix in G is, and then these two have to commute. And I'll explain to you like a little bit that this is kind of like a not quite the flag DG Hilbert scheme, but it's kind of a close cousin. And so this is going to be kind of a direct translation of the triple graded homology construction. But it also has a nice, so there is going to be some kind of like commuting square here. Okay, maybe so I could say there's a map going here, which I'll also tell you what is later. And this space turns out to be exactly equivalent to this kind of matrix factorizations that Oblomkov and Osansky defined. And this also has a very famous break group action due to Bezukov-Likov. And Risch. So here I'll maybe, if my matrix is better, I'll write the image of this as O beta. All right, so basically this, like the upshot of my entire talk is kind of like this this triangle and this. All right, so let me first start to like at least give you the like basic definition of what is this kind of matrix factorizations, because it's maybe not a super standard object. I mean, most people like kind of familiar with working with coherent sheaves, but matrix factorizations are kind of maybe a little bit less standard. So let me tell you where they are, what they are. So here you just, well, a G-equivariant matrix factorization. I'll like take any algebraic group. Doesn't have to be GLN. This is like kind of the only section where G doesn't have to be GLN. And then you take a smooth complex G scheme and you take a regular G invariant function. And then your matrix factorization is a quadruple. So it has two G equivariant vector bundles. And then we have this kind of like funny differential thing. So you can imagine that these are like put them in a complex where you just repeat this. So you like have a periodic complex alternating with m-1 and m0. And then these you should think of kind of the differentials, but instead of squaring to 0 as like regular usual differentials should, we ask them to square to multiplication by this function. And well, you can like imagine what the morphisms will be. So when you take this, you will like see that maps should have differential 0, because if you have like multiple maps between these, then you're gonna mess up this if you don't have differential 0. So this thing is an honest DG category, even if we had like some like funny kind of differential going on here. This is a GG category, and we can take its homotopic category. And then we mod out by what's called locally differentiable. It's not super important what it is. Okay, so it's locally contractible means that there exists an open cover in the smooth table, such that when you take your matrix factorization and restrict to each of them, you get something equivalent to 0. So it's not super important. And in the case where x is affine, you don't need any quotient at all. So there it's just void. Okay, so this is kind of like my favorite version of matrix factorizations. And in the name of complete honesty, I should say that this is not exactly what Oblomkov-Nosansky is doing, because they have the same construction kind of, only they have a slightly different way of imposing equivariance, but there's a direct way to relate these two. So I'm not going to, and this is just a bunch of like boring technical stuff. So in the interest of time, I'll like completely ignore this and just say these two things can be made to fit each other. So you can just take this as your definition, since it's also the fastest to state. All right, so the first kind is that these two are equivalent as monoidal categories. So this has a monoidal structure, which is maybe not so easy to see in this formulation, but it's there, and it comes from a slightly bigger space. So this is kind of like a direct consequence of a like paper I had with Zagaripov. This equivalence. The interesting thing is that this is a model equivalence, and these so the braid group action that Oblomkov-Nosansky constructed using their fancy string theory is exactly the same as Bezukhavnikov and Risch constructed by completely different means. So when I asked Roman about it, I got some p-adic explanation, and this is also something that works in positive characteristics. So it's a case of people doing completely different things for like pretty different reasons and ending up with exactly the same result. Okay, so this was kind of the commutativity of the first part. Okay, so let me look at this and okay, so how could you invent something like this? So why does Steinberg, which is this like standard my favorite categorification of the affine Hecke algebra, where does it show up at all? I mean, it's like from the get-go, it just looks like kind of like as pulled out of a hat as this one might. So what does these constructions have to do with each other? And so the standard way to get into geometry from between circle bimodules is not is to these D modules using Webster and Williamson, saying, okay, so this is the simple circle bimodules corresponding to my a W. So for the purpose of like dealing with root complexes, you can like mentally replace this W by just S. This is the only one we need. I just wrote it for general W because it's true for general W. So why not state it? Okay, so it says that this like thing can be defined, can be calculated as hypercohomology of an IC sheaf. So B times B equivariance would say that we have a sheaf, which is the IC sheaf corresponding to BWB, that's it, on this space G mod B mod B. And then the next thing they tell us is that if you want to this Hochschild homology, which was like the next like difficult part of calculating triplet graded homology, then this has a very natural relation to this. You just take, instead of taking equivariance between two copy of G, we take equivariant respect to the diagonal copy. So with this diagonal inside here. So if so we can think of this as just if we want to go from circle bimodules and take only what we need to do is we need to pull back along this projection map, and then we get this is exactly gives us the correct IC sheaves, and then to get a cohomology, well, that just responds to pushing forward to a point. So this means that if we like play this game this way, then doing this will basically just give us a cohomology of a pullback here. So I originally worked with it, and I wasn't super excited about like what I got, not because it gave something nice, but it just said, okay, that's nice, but whatever. But the interesting thing is what happens if I take a detour. So instead of pushing directly forward to a point, I push forward to the G quotient, and then I push forward to the point, because then something interesting happens when I try to play this associate graded game. And this is where my Hilbert schemes are going to show up. Okay, so maybe just so this is like a different way of writing the same varieties, which is maybe more transparent when you want to like see what its cotangents are. Okay, so the main engine of going from here into the land of coherent sheaves is kind of this theorem, Cartesius and Kanstrup, which says that we have a nice monoidal functor. So here I should technically write this is a module over the Riesz algebra, or I could also like say some words like mixed Hodge structure, whatever. The thing is I need a D module which comes equipped with a filtration, but I'm going to, for the purpose of this talk and the reviewing of this talk, to completely ignore that and just say, well, this kind of functor exists. And also I need not exactly just this functor, but I need a G-equivariant version of this, but that can also be dealt with. So I just stated the version that appears in the literature, but it can be extended to what I need to do because I want to, the game I want to play is I want to feed it this correspondence, because there's a very nice relation with what happens with the associated graded when you pull back and push forwards. So the general idea here is if I take, well, the cotangent space of a point is just a point. So if I take associated graded here, like nothing at all will happen. So the idea is, so now if I just like commuted my way over here, something interesting happens. So then I could take this and get into my land of coherent sheaves, and then at some point I'll run a construction and get to just come on to a point here where the associated graded would do nothing. So what do we get when we play this game? So each time when you have a push forward or pull back, you get a correspondence. So this correspondence is kind of is a fiber product actually, because this correspondence I'm writing here is actually what you get from these two. So you get a correspondence from this pullback and a corresponding from this push forward. And if I like collect these two together, I get this big correspondence. And so if I just push forward to a point, that will also give me a correspondence, and this correspondence will be this one. Okay. So what are these things? So the upshot of this is that indeed the space is nothing else with like my Steinberg mod G, which is the space that appeared here. So this is like kind of, I take my braids in my D module country and then I lift it up onto Steinberg here. And equivalently to where Oblomkov and Lasansky is doing their stuff in terms of matrix factorization. And then this thing, so here I'm again putting this L here to indicate that I take this kind of fancy commutativity relation, which is the same kind of way we imposed commutativity on the DG flag Hilbert scheme. And it turned out that this is very close to the flag Hilbert scheme. But this one is even more well known in that sense, since this is, so this is a question of, we have two matrices commuting with each other. So this looks a lot like our Hilbert scheme. So there is of course some differences, because here for my Hilbert scheme, I had two elements in my Lie algebra, so two general matrices without any invertibility condition here. And then the Hilbert scheme has this cyclic vector, so this extra vector which we imposed the stability condition on. But so the thing is that you can take this and then you can add a framing, and then you can embed, since we are talking type A, we can embed our group into our Lie algebra. And when we take the stability condition, then lo and behold, then we end up on the Hilbert scheme. And this is kind of like where it's Oblomkov and Lasansky they're doing. They're really like kind of working in this setting, and then they are like making their way onto the Hilbert scheme this way. And this is kind of a cousin, but not quite as easily relatable, because here we're really depending on this being the group and not the Lie algebra. So it won't be, it can't be exactly the Gorskine-Rasmussen conjecture, but it's kind of close. Okay, so this is kind of what I just said, that indeed, if we run this process, we end up with triply graded homology. And also, like, well, one thing we note is that one thing one can observe is that the Rukia complexes actually turns out into the Vesco-Karnikov breach break-grain ratios. So this is kind of like another way. Why does Oblomkov-Voltansky work? It's because they're like their matrix factorization is exactly a Rukia complex. It's just like what this like general construction gave you, and then you kind of work with this. And the rest of this will also, so they have this churn functor is kind of going through this correspondence, and like the last thing going to the triply graded space is kind of this correspondence. And maybe one nice thing is that, like, why does it work out so nicely? Because these break generators, even when you take a big convolution product, they're still coherent sheaves setting in 1 degree, as opposed to this kind of like giant complex you would always usually get when you do Rukia complexes. Okay, so I'm out of time, so perhaps I should stop here instead of talking about other types. Essentially, that's it's essentially in other types you can do exactly the same thing, but you will need, the only question is, so what's the nice space you would replace the Hilbert scheme by? But I think I should stop here. So thank you very much.
Thank you, Tina. Let's thank Tina. And do we have any questions for Tina?
Yeah, so do you know if in these other types, these varieties are close to the quasi-commuting variety?
Yes, so they're,
yeah.
So, well, in the sense that you won't have exactly the commuting variety. The commuting variety you're probably thinking of is like 2 copies of the Lie algebra, right?
Mm-hmm.
That's probably the one. So no, in general, you will very much need to have an element in the group and an element in the Lie algebra. I mean, in type A, it kind of works out because you can embed your group into a Lie algebra, and then you impose this the stability condition and kind of get lucky that it works out. But if you want to do another type, well, you don't have that embedding, so that's like completely falls apart. So if you do want to do other types, you really do need to work with the commuting variety, but with the group instead of the Lie algebra. And then you can play games. You can try, okay, so Hilbert scheme is a GIT quotient of this with the framing. So if you have like a non-trivial determinant, I mean, you need a character to do a predictive DIT quotient. You could try to do this, or another option, you could try to restrict to the regular group elements and do the same thing, because then if G is simply connected, then your replacement for the Hilbert scheme will be smooth and symplectic, and it'll be something that is like nice to work with still. But yeah, there might be other like nice ways to like replace this derived commuting variety with something that is easier to work with, something with like it's an honest, non-derived smooth space.
I mean, in the Hilbert scheme, there is the quasi-commuting variety, right? But I don't know if that's something that is defined like in other types, or that makes sense in other types. Yeah.
But for the commuting variety, you just mean like throw away the vector, right? And just
no, I mean matrices whose commutator has rank 1, I think. That's like easier than the commuting variety somehow.
Oh, okay. I don't know. I don't know if there's a connection for this.
Yeah, thank you.
I mean, you're kind of like, this is kind of a weaker requirement than like requiring them to commute on the nose, because you're working with the derived space, so you're like requiring them to commute up to higher homologies in some sense. So this is like something that is slightly weaker, but not like, I don't think it's something that would be something you can write in the sense of like something with the commutator having rank 1.
Thank you.
Hi, Tina. Can I ask about how the current status of the affine GNR conjecture and whether your tricks will work there? So this is like relationship between gate score central sheaves and stuff on the commuting world.
So I mean, in some sense, I feel like this is more naturally like the affine version of GNR, because that's essentially what you're doing. You're taking your like finite world, you're like kind of like artificially inserting it into the and then you're like playing your games, doing everything, because this is kind of going to the center. So something that kind of is going to like the story of character sheaves and such. So this is kind of like naturally an affine GNR more than GNR. Like the GNR is kind of like when you need to like get back to your, I mean, you need to like kill off the like the cotangent pieces you kind of like artificially inserted here. I tried to do this for a long time, trying to show there was a link invariant, and then completely failed. And in the end, I realized it's not. So yeah, you really need to go back to your affine world. You can play around, to your finite world, sorry. You can like play around all day in your like affine story, but by the end of the day, you need to go back to the finite piece. So you're essentially taking an affine GNR and then like pulling it down to get a finite one. But
I guess what I'm interested in a little is in part B of your theorem, you sort of match up the braid generators on sort of one geometric side of the story with a root gate complex on the other. Is this like a computation that you can imitate in the affine case to match up certain things with gate score central sheaves to compute to match up the circle side with the geometric side?
I don't know, basically because I don't know a lot of about affine circle bimodules.
Okay.
But I mean, it's certainly very much, I mean, this is literally just going to the cosender. So there's no way this is not connected to that. And this is, you might say this would be naturally something that should be called like something related to affine circle bimodules, because it came from something that is supposed to be circle bimodules, and then you take like affine version of it. And then hopefully this is related to affine circle bimodules. Yes. Which I presume categorifies the affine Hege category. Right. Hege algebra.
Yeah, there's like another diagram you need, another space you need to put in there to get the gate score central sheet functor. But well, that's it. We'll stop asking this question. Thanks.
Okay, do we have any more questions for Tina? Okay, if not, let's thank our speaker again.